the dependence of the energy of an interaction of the type and how it compares versus lambda phi to the fourth. What was the answer? What is the answer?
When like the energy over lambda to the fourth in comparison with the other.
Okay, so this one like what?
No, it was like lambda.
Like lambda?
And the other one like lambda energy over big lambda to the fourth.
Okay. So what was the point of this exercise? No. Oh, sorry. Yes. So the point of this exercise was to show that, as already said in class, that operators of this type, which are irrelevant because the dimension of this guy, the classical dimension is 8, right? It's precisely to show that if you look at energies much smaller than some cutoff, that this term is very subdominant with respect to this one. So if you're a very low energy physicist, that guy gives you a very subdominant effect. But more precisely, I mean, what was the coefficient here? I mean, in terms of the Mandelstam variable? Did anyone was able to do that?
Was that plus E squared plus Q squared?
Yeah, exactly that. But, I mean, do you understand why it is that? Or yeah. So actually, I think Anna will go through, or this afternoon the tutorial you will go more carefully through it. But if you do it carefully, and you compute the scattering or 4 or 5 quanta, the amplitude, the transition amplitude is precisely given by this lambda s squared plus t squared plus u squared, which are the where st and u are the Mandelstam invariant. Okay. So there are no questions then? Good. So let's continue. So hopefully today I'll finish the kind of motivation background part of the course, and tomorrow we'll start with this more systematic development of the subject. But before I start, let me just remind you a little bit what the story yesterday was. Yesterday I was telling you that that the ideas of renormalization group give us a systematic framework for organizing the low energy effective description of any physical system, given some basic input, which is that you have some information about what the low energy degrees of freedom are and what the symmetries are. And the logic of the construction told us that in principle you have to write down all possible interactions given the degrees of freedom consistent with the symmetries, where these OI are all possible interactions you can write down given the basic degrees of freedom. And if you want to make, sometimes it's useful, like in this exercise, to introduce this ultraviolet cutoff in order to make manifest work in a frame where this coupling constant is dimensionless. And then this guy will be weighted. If this operator has dimension delta, then this interaction is suppressed by a power of d minus delta, I, right? And just by this simple dimensional analysis, which is improved by when you do a more careful analysis using the renormalization group equations, like Alan-Szymanczyk equations, what you find is what we said, that if the operator has dimension bigger than delta I, then this operator is irrelevant or suppressed at low energies. And if we're interested in the low energy, large distance properties of your system, we can focus on the operators that have dimensions bigger or equal than delta, which are the ones that dominate the long distance physics. And I also made the point that even though you naively think that you can start with a given lambda phi to the fourth theory, quantum mechanically you always generate all possible interactions by virtual effects. And this is something that happens even in lattice systems. Where actually many of these ideas of the renormalization group came from thinking about the large distance properties of spins in lattice systems like the Ising model. And probably, Kadanoff, which was essentially the inventor of these basic ideas. In that framework, you can also just start with some lattice system and ask what happens to the system as I probe it at larger and larger distances. And essentially what you find is exactly the same thing, that you generate all possible interactions between the spins. So even though you started with, say, Ising Hamiltonian that has only nearest neighbors interaction, if you ask what happens at very large distances, and essentially what you find is when you integrate out, when you eliminate the very short distance degrees of freedoms that you're not going to be able to probe because you're looking at large distances, you will be generating all possible interactions between spins. And in particular, you'll generate not only nearest neighbor interactions where the coupling constant will flow, but you will also generate interactions between next to nearest neighbor spins and so on and so forth. And that's where this idea of the flow in the space of Hamiltonians comes from, essentially. And this is just another language of saying exactly the same thing. That you start with some physical system, you go to large distances, you generate all possible interactions, and these interactions flow with the energy scale that you're probing. And dependence of the couplings on the energy scale was determined by the beta function equations. This tells us how different couplings here depend on the energy scale. And the other thing that we saw is that in the space of flows, in this space of field theories, there are special points where the beta function vanishes. You have zeros of the beta function. And since the theory, at those points, by construction, the theory is invariant under scale transformations and under mild assumptions, under conformal transformations, these fixed points are described by conformal invariant field theories, which is the subject of this course.
Jaume?
Yes?
Delta I is the dimension of the operator.
Yes.
So it should be the other way around, right?
So this has to be dimensionless. So yes. Thank you. Yeah, I mean, the reason you fix the dimension this is that you have mass dimension minus d, which cancels this one, and it has mass dimension delta I, which cancels this one. Yeah,
so it is d less than.
I made a mess here. I meant exactly the opposite, yes. Thank you. Good. Okay, and then what we saw is that in the space of field theories, we have these fixed points floating around. You can have, in this case, imagine you have 3 fixed points. You have Cft1, Cft2, Cft3. And you have nice flows between them that are controlled by turning on some relevant operator. And that allows us to go from one fixed point to one fixed point. Okay? And again, any field theory here can be thought of as a perturbation away from a conformal field theory by turning on some operator in the conformal field theory. Okay? And then I very quickly at the end, and I don't want to spend too much time now on this, but because I'll come back to it later, but let me just say a couple of things, is how do you construct a non-trivial conformal field theory? And this, I mean, historically, it was very important in the development of the subject. And it's not only important conceptually, it was also important in practical matters for being able to calculate the behavior of statistical systems near a phase transition. And this was this Wilson-Fisher fixed point. And here the idea is kind of simple. Let me just tell you first the general idea, is that if you start with a theory that has classically a marginal coupling lambda. So it means that classically is dimensionless. But then we know that quantum mechanically, due to virtual effects, this coupling will acquire some non-trivial running, beta lambda. And there are essentially two behaviors you can have, unless the theory happens to be exactly conformal, which is rare, except in supersymmetric theories. The beta function can be positive, in which case that means that since the variation of the energy with of the coupling with the energy increases if the beta function is positive, these are theories where the coupling grows towards the ultraviolet. And an example of such a theory is exactly lambda phi to the 4. Or the beta function can be negative, in which case lambda grows towards infrared. These are also sometimes, you must have heard this word of asymptotically free. And an important example of such a theory that has an asymptotically free coupling constant that grows towards infrared is Yang-Mills, called the Yang-Mills theories. Okay. So the basic idea of constructing this Wilson-Fisher fixed point is to say that let's not study the theory. So this theory has a marginal coupling lambda at some given dimension. Okay. So for lambda phi to the 4, say in 4 dimensions. It's only in 4 dimensions that the theory is classically marginal. But now imagine you do the following thing. Imagine you want to study the theory. You analytically continue the theory in dimensions. You treat the theory not in 4 dimensions, but in 4 minus epsilon dimensions. Whenever you increase the dimension of space-time, a given operator becomes more relevant. Okay? So going from 4 to 4 minus epsilon, essentially what it accomplishes is to make lambda phi to the 4th go from a marginal operator to a relevant operator. Okay? So that means that even classically, when you compute, since now lambda has a non-trivial dimension, it means that when you compute the running of the coupling, it has the usual one-loop contribution. Okay, the usual quantum contribution that you computed here. That usually for example, in lambda phi to the 4th, you've computed this at one loop. You know that the beta function there is non-zero and positive. So you'll have the usual one loop running, which in lambda phi to the 4th is something like 3 lambda squared divided by 16 pi squared plus higher order correction, lambda cubed. But now since lambda all of a sudden has mass dimension epsilon, which means that it's a relevant operator, has positive mass dimension, you have a contribution to the variation of the coupling, which just tells you precisely that lambda now all of a sudden has a classical engineering dimension. Okay? And the idea of these guys was that by doing this trick of making lambda phi to the 4 slightly marginal by going just below 4 dimensions, now you can find a zero of the beta function, because you have a theory which had a positive beta function due to virtual effects, but there's a contribution from just dimensional analysis. So now you can, by making epsilon sufficiently small, you can try to find a zero of this beta function in a regime where the value of lambda at the fixed point will still be very small, and you can trust perturbation theory. So if you plot beta lambda versus lambda, it starts at negative, but then it picks up the positive quantum contribution, and there is a non-trivial fixed point here, lambda star. Okay? And here, by playing this game, you fish out this conformal field theory, which is the Wilson-Fisher conformal field theory, which has different properties than the conformal field theory that you started with. So this conformal field theory was just a free field theory. This one is not a free field theory, and in particular, if you compute correlation functions of operators in this theory and in this theory, they have different behavior. They have different power law behavior. And for this particular case, this value of the coupling lambda star is something like 16 pi squared over 3 times epsilon. And there was a big industry in the 70s where these ideas were developed to really calculate the correlation functions of observables which you associate to different thermodynamic quantities corresponding to the critical behavior described by this conformal field theory. And essentially, by doing calculations around this fixed point, people were able to predict the critical exponents for magnets, for example, by doing something which is very wild. So you do a power series expansion in epsilon. You resum. Actually, you should ask the previous lecturer to explain you why this makes any sense. And then analytically continue to epsilon equals 1. And you find miraculous agreement with the experimental values for the critical exponents. And people got Nobel Prizes because of this. And actually, later I'll give you an example of some of the critical exponents that you will calculate from the Wilson-Fisher fixed point and compare to some of the experimental values. This idea, and we'll come back to it later when we discuss how to construct non-trivial conformal field theories in different ways, is very generic. So one way you can try to find a perturbative conformal field theory, which is governed by a coupling constant which is still small, because originally lambda was small, is always by killing the first two terms in a beta function, either by changing the dimension of space-time, so that you have a classical contribution which is compensated by a one-loop contribution, or you can do something else. In some situations, you can compensate the one-loop contribution with, say, the two-loop contribution, and still find a zero of the beta function, where still the coupling constant at the zero will be very small. And later in the course, I'll give you an example of that. That happens actually in gauge theories. These are called the Bank-Zaks fixed points. But for the time being, this is sufficient. The reason I wanted to mention this is that this really was very important in the development of conformal field theory and its applications to statistical physics. And later I'll give you some numbers just to see that it's pretty impressive how well it works. Okay. So now what I want to do is actually give you a more of a... So far the motivation that I gave you for conformal field theory is more based on our conceptual understanding that it plays in our view of quantum field theory. And, but there's actually more direct use of conformal field theories for nature. Okay? So, and I'll give you a couple of examples. And this alone justifies the study of these subjects, even though, as a theoretical physicist, the fact that it plays such an important role of our understanding of the space of field theory, it was also sufficient for me, but this definitely, if you're a more pragmatic person, this definitely is also a very important application of conformal field theories. So essentially, two traditional applications of conformal field theory in nature, which is very closely related to the one I've been discussing there. One is to critical phenomena in statistical mechanics and statistical physics. So this is, so I imagine that you have seen some of this in your statistical physics courses. So I'll just be a little bit brief about this. And essentially, this critical phenomena is the description of a system. It can be a magnet, it can be... I'll have in mind always the Ising model as a prototype, but which describes magnetism. Description of a system near a continuous phase transition. Okay. Sometimes it's called second order, but it can be higher. That has the property. So usually a physical system has some correlation length that tells you the length scale over which the basic degrees of freedom are correlated. And the basic property of a continuous phase transition is that by tuning the experimentalist, by tuning knobs in the experiment, like temperature, pressure, magnetic field, and so on, you can tune those parameters such that the system has, the correlation length of the system goes to infinity. So this psi is the correlation length. But you can tune parameters such that the correlation length goes to infinity. And when that happens, you precisely hit one of these critical points in the phase diagram of the system, where the system actually exhibits fluctuations at all energy scales, or all length scales. And therefore, since you have essentially scale invariance, because you have fluctuations at all possible length scales, these systems at the critical point are described by conformal field theories. Okay? And different types of phase transitions are controlled by different conformal field theories. Okay? And essentially, the behavior of the thermodynamic quantities. So near a critical point, the thermodynamic quantities like magnetization, susceptibility, and so on, exhibit a scaling behavior which is characterized by critical exponents that tell you how these quantities behave as a function of the control parameters as you approach the fixed point. And the way that the quantities behave as a function of the external parameters is parameterized in terms of the critical exponents, which are directly related to the dimensions of the operators in the conformal field theory. So if you want to see whether your conformal field theory describes the critical behavior of certain statistical system, the thing that you have to do, one of the things that you have to do, is to study the exact dimensions of operators at the fixed point and compare the scaling behavior of the various thermodynamic quantities that you can compute from the conformal field theory with the critical exponent that you measure. Okay? And later in the course, we will, especially in 2 dimensions, we will be able to compute exactly the operator dimensions in an infinite class of conformal field theories and show that these conformal field theories describe different universality classes of critical behavior. By universality classes, I mean different types of scaling that physical systems can have. So if you have a system that has, like the Ising model, has a particular type of scaling behavior as you approach a critical point, but there can be other systems where you have, instead of two component spins, you have higher component spins that have a different critical behavior. And then there is another conformal field theory that would describe that. And the types of different scaling behavior that you can have are precisely the different, the jargon is these are the different universality classes. And each universality class has a corresponding conformal field theory. Okay?
I have a question.
Yes.
How does this fit in the picture of our theory space? So there are the
So the
universality classes.
Universality classes are precisely this would describe one universality class.
Okay, so the fixed point.
Yes. And one way to think about, so usually in order to hit a fixed point, you have, experimentalists have to very finely tune the parameters. So for example, you're at the Curie temperature and you have non-trivial phase transition. And from this language, what that means is that you have to tune, for example, here, this operator is relevant, here, this fixed point, right? It's flowing away. So in order to hit this fixed point, and this guy, in the simple case, would be like the coupling associated to the mass square operator, m squared phi squared. So in order to hit the fixed point, what you have to do is tune very carefully the trajectory of the RG flow so that you're exactly sitting at the fixed point. Even though this direction is repulsive, if you start a small distant epsilon away from it, it will keep you out of the fixed point and it will not be conformal anymore. But the experimentalist has the knob that can precisely tune the coefficient of this coupling to be 0, so that you're sitting precisely at the conformal fixed point. So hitting fixed points requires extreme fine-tuning of relevant operators, because you have to make sure that relevant operators like to keep you away from conformal fixed points. So if you want to get the fixed point, the experimentalist has to tune the pressure, the temperature, and the magnetic field so that you're there, essentially. And that's, in the language of field theory, what you're doing is you're tuning to 0 the coefficients of the relevant operators around the fixed point.
Is it possible, I mean, to tune it that much precise?
Well, experimentalists do it.
So what about the uncertainties and like that?
Sir?
Well, we have uncertainties. I mean, well, to me, it's not possible to do it like, I mean, with infinite precision.
Well, there's nothing like infinite precision, but definitely, if you see the plots of magnetic susceptibility as a function of temperature near the Curie transition, you'll see that the guy blows up like crazy. So of course, it will not go all the way to infinity, but it will have absolutely clear divergent behavior as you approach the critical point. I mean, you're always restricted by resolution of the experiment that were done and those kind of things, but definitely it exhibits the scaling behavior beautifully. Yes?
So do we want to think that every fixed point corresponds to a CFT, or are there fixed points that would not correspond to a CFT as well?
Yeah, so I get it in 2 dimensions. So this is what I discussed yesterday. So for a general, in general dimensions, there is no theorem that a scaling. So definitely the theory is a scaling invariant, but not necessarily conformal invariant. So it's not known in dimensions higher than 2 whether a scaling invariant implies conformal invariant, but it's very widely believed that it is true. And in 2 dimensions, there is a theorem by Zamolodchikov and Polchinski.
So you're assuming that it's relativistic. No.
Well, so in most of this course, I've been assuming relativistic field theories, yes. If the system is non-relativistic, then it will be controlled by a different conformal symmetry. That is also very interesting, but right now I was mainly concentrating in relativistic theories. And actually, in that case, it's also not known even in 2 dimensions whether a scale invariance of the non-relativistic system implies non-relativistic conformal invariance or not, even in 2 dimensions. And that's an interesting question that I think can be answered but hasn't been answered yet. More questions? Okay, so that's one traditional important setup where conformal field theories are central, which is critical phenomena at non-zero temperature. So these phase transitions, which I'll describe them a bit more detail later, are controlled by, or by thermal fluctuations, or driven, the right word, driven by thermal fluctuations. Because these systems are at non-zero temperature, okay? Now, another type of interesting systems that exhibit critical behavior at 0 temperature go under the name of quantum critical phase critical phenomena. So these are quantum systems. So that's the difference between quantum and classical. These are driven by thermal fluctuations. In the quantum system, you're at 0 temperature. And the transition is driven by quantum fluctuations as opposed to thermal fluctuations. Okay? And essentially what can happen is the following. You can have a quantum Hamiltonian that has a certain spectrum. So you have a ground state, and then you have excited states. E1, E2, and so on. Okay? There is an important quantity in these quantum systems, which is called the gap, which is the gap between delta, between the ground state and the first excited state of the system. Okay? Now, what can happen in some quantum systems is that this delta, again, is a function of some control parameters, G. So here also you had control parameters, right? You had temperature, you had pressure, you had magnetic field. Here you also can have some control parameters like magnetic field. And then what can happen is that you can tune this control parameter such that the gap between the ground state and the first excited state closes, and the gap goes to 0. Okay? That means that the system, well, it's gapless, and the correlation length also goes to infinity. Okay? So these guys are also described by conformal field theories. And Giffrey is an expert on the properties of those systems. And later I'll give explicit examples of different models, both in category 1 and category 2, that are described by non-trivial conformal field theories. And later in the course, we will completely solve those conformal field theories and therefore be able to predict the correlation functions of the various observables in these interesting systems. Okay, so let me now maybe go in a bit more detail in each of the two cases. Oh, sorry. So I already said that an important quantity that characterizes the range of correlation of your microscopic degrees of freedom is this notion of correlation length. And now we want to start characterizing more carefully how do we extract what the correlation length is given the correlation function of our basic observables. Okay? So this correlation function is obtained from the two-point function of the basic variables of your system. Okay? So, for example, in the case of the Curie transition, where you go from antiferromagnet to a ferromagnet, the basic variable is going to be a spin variable. Okay? Or in the liquid-gas transition, this will be the density. Okay? I already mentioned that yesterday, that these are the basic macroscopic variables that drive the fluctuations in these systems. Then the correlation method essentially tells you how these two basic variables, and this is the connected correlation function. So you want to know, if I take these two basic variables and you separate them very far apart, how much they like to be correlated. And that typically has an exponential follow-up that goes with the distance. Okay? And this psi is exactly the correlation length. Okay? And this psi is a function of the external parameters. the experimentalist controls. And I already said that the thing that's important for this classical critical phenomenon in physical mechanics is that psi goes to infinity as the temperature approaches, say, the critical temperature of the system. And therefore, as you approach the critical behavior, this exponential fall of behavior is replaced by power law behavior. Okay? In some sense, psi is a length scale in the system, and if you go to the point where the length scale disappears, you have no longer any length scale left. So the only kind of behavior that you can have is a power law behavior. And we will see, I mean, more systematically when we start discussing the form of correlation function in conformal field theory. This power law behavior is exactly the behavior of correlation functions in conformal field theory, as in conformal field theory. Okay. So let me give you just two basic examples of, one example of a system that has this. Imagine you are, which is this Curie transition. So this is the phase diagram. You have control over the magnetic field and the temperature. For low temperatures, there is a first order phase transition around this line, across which the magnetization jumps discontinuously. Okay? Essentially, the system has a certain symmetry, and depending on the sign of the magnetic field, the spins would like to align up or down. Since you have a discontinuity across this critical line on the magnetization, remember the magnetization is roughly speaking, is a first derivative of the free energy. Across this line, you have a first order phase transition. Okay? But first order phase transitions do not have infinite correlation length. Okay? It's only at the end point of this line of first order phase transitions, at the Curie temperature, that the correlation length goes to infinity. Okay? And it is the physics near this point that's described by a conformal field theory. Okay. And of course, at very high temperatures, the magnetization here is zero. Okay. Very good. So the kind of systems that are described by at finite temperature described by conformal field theories are always of this type. You're going to have some point in your phase diagram where the critical length, correlation length goes to infinity. And typically, those guys are always at endpoints of a line of first order phase transitions. But in this course, we will focus on the behavior at the fixed point and near the fixed point. Okay? More precisely, the behavior of a phase transition. How do you know that there is a phase transition? Essentially, you know it by detecting a non-analyticity, so phase transition is encoding a non-analyticity as a function of the control parameters of some thermodynamic quantity. Okay? So the basic thing that you compute when you have a physical system like this is you compute the partition function, where you sum over all microscopic variables. In that case, could be the spin variables. Let's call them S or sigma, because I call them sigma there. And then you have the exponential of the Boltzmann factor, where you have some energy function, which is a function, of course, of the spin variables, or the variables of your microscopic Hamiltonian, as well as the control parameters, like magnetic field and so on. Okay?
Excuse me.
Sorry?
What do you mean by power law behavior?
It means that if I compute the correlation function between phi x, this could be magnetization. And I look. So the scale, it's a power law with respect to the coordinates. So notice that you had exponential behavior. Here you have just homogeneous behavior with respect to scaling. That's what it is. And this is the hallmark of scaling invariant theories, that correlation functions have this power law of behavior only. Okay? So this guy is just the free energy of the system. And once you have the partition function as a function, or the free energy as a function of the control parameters, then you can compute all the standard thermodynamic quantities. So let me just mention a couple that are relevant here for this simple example. So you can compute the magnetization, which, as I said, is kind of roughly the first derivative of the free energy with respect to the magnetic field. Or you can compute second derivative, which is magnetic susceptibility, which is the first derivative of the magnetization with respect to the magnetic field. Okay. And essentially, the different types of phase transitions you can have tell you whether the singularity or non-analyticity in the thermodynamic quantity happens in a quantity which is obtained from the first derivative or the second derivative of the free energy. So the first order phase transitions I was talking about here that go across this wavy line give you this continuity in the magnetization, which is the first derivative of the free energy. So jumps in M are the characterization of the first order phase transition. While singularities in the quantities which are second order of the free energy are these continuous phase transitions. It can be second order or higher. Okay. So now we want to characterize the behavior of these physical quantities near the critical point. Okay. So near the endpoint of the line of first order phase transitions. So as I said, near the critical point, the first physical thing that happens is that the correlation length goes to infinity. So just from that, you know that it has to have the following scaling behavior. It tells you that it has to blow up as a function of t minus tc to some negative power nu. Okay? Because as you approach to the critical point, the correlation length blows up. But it blows up in a very characteristic way, some power law behavior. And these numbers are the whole subject of critical phenomena. And these are called the critical exponents, which, as I said, tell you how different thermodynamic quantities or correlation lengths blow up, not necessarily blow up, but behave as you approach the critical point. Then you can also introduce a critical exponent for magnetization as you approach the critical point. So the magnetization goes to 0 as you approach the critical point. It doesn't blow up. That's why I didn't put a minus sign here. But it goes to 0 at a very specific rate. It also goes to 0. It goes to 0 as a function of the temperature, but it also goes to 0 as a function of the magnetic field. Okay? So you can define also a critical exponent of how the magnetization goes to 0 as you tune the magnetic field to 0. And now the guy that really blows up is the heat capacity, which is also like the second derivative of the free energy, essentially. As you approach the critical point, also blows up. Well, you can have the heat capacity, which is the second derivative of the free energy with respect to temperature. Or you can also have something blowing up, which is the magnetic susceptibility, which is the second derivative of the free energy with respect to the other control parameter, which is the magnetic field. So this blows up like that. So that's why I have a negative exponent. And the last, okay, there are many, but the other important kind of critical exponent that I want to describe is what I wrote essentially here, is the correlation function between the basic variables in the system, the spins, and these exhibit a peculiar, well, not so peculiar, power law behavior. So if this theory was, okay, let me define it first. So this is again a different critical exponent. If the system was free, in a free field theory, this would be eta. Eta would be 0, right? Because this is precisely the behavior of a scalar field in free field theory. But at a non-trivial fixed point, the scaling behavior is shifted by this eta, which sometimes is also called the anomalous dimension. And the subject of critical phenomena is essentially the subject of measuring and computing these quantities, these critical exponents. Okay? Okay, any questions about this? This should be mostly known to you, hopefully. If not, I'm happy to elaborate. But, so let me give you kind of nice macroscopic Hamiltonians that want to model this kind of phase transitions, from which whose critical behavior we will study later in the course. So there are many, many, many models that you can write down, say in 2 dimensions between spins that interact. You can put spins on a lattice interacting in different ways. Also, the spins can have different components. You can have 2 components. You can have S component. And there's a whole rich landscape of phase diagrams like those ones, where with fixed points sprinkled in the middle of the phase diagram. Unfortunately, in 2 dimensions, we essentially know how to compute all the properties of those fixed points using conformal symmetry. Conformal field theory techniques that will be the second part of the course when we focus in 2 dimensions. In higher dimensions, it's much harder to solve conformal field theories, and then we have to resort to these funnier perturbative techniques and try to compute just in some kind of perturbative expansion and resummation. But in 2 dimensions, as we will see, conformal symmetry is so powerful that just allows us to solve the theory completely and get precise expressions for all these critical exponents. So a nice example, microscopic Hamiltonian, spin Hamiltonian, that wants to describe the Curie transition is the Ising model in 2 dimensions. This historically also played a very important role in the development of, in the interplay between condensed matter physics, field theory, and critical phenomena. And this is a system that has, as you know, a Hamiltonian of this type. So you have some energy per bond times the spin. So you have a lattice in 2 dimensions. At its vertex here in the lattice, you have a spin. And this spin can either be plus or minus 1. There are, of course, other models where sigma can take more values, and those are interesting too. In fact, they're interesting. And you have interaction between near neighborhood spins. This funny bracket means that you only have near neighborhood interactions, okay? So there are terms in the Hamiltonian that couple this spin with this spin and that spin. But for example, this guy doesn't have a direct interaction with this guy, which is too far away. It's 2 sides away, okay? And essentially, you can try to solve this model, and people did, and it's actually rather non-trivial to solve this model in general. And essentially, the way you would have to solve it is by computing in some clever way the exact partition function of the system as a function of the temperature, and you can also add a magnetic field if you want. And then find out that there is a critical point in the phase diagram. And since you know how to compute the thermodynamic quantities exactly as a function of the temperature and the magnetic field, you'll be able to extract this. And people have done that. It's a really heroic computation. The thing that's beautiful about this picture of field theory near the critical point is that we can get these numbers much more easily just by directly focusing at the behavior of the system at very large distances, where we don't have to deal with these more complicated microscopic Hamiltonian, and we can just use ideas of field theory and universality to just get directly the numbers. Okay. So this model famously has a critical point. At a particular value of a dimensionless parameter, which is essentially the ratio of the energy scale divided by the temperature, at a value of this coupling, where this guy, I think it's a factor of 2 here, where this value is 1, you have a critical point. Okay? And this will be described, as we will see later in the course, by what's called the Ising conformal field theory, two-dimensional Ising conformal field theory. Okay? And for that model, we will compute the correlation functions of the various observables using the Ising conformal field theory. Okay? Very good. So this was an example of a microscopic Hamiltonian that exhibited the first type of critical behavior that was driven by thermal fluctuations. Now I'll give you quickly a couple of examples of quantum Hamiltonians in one spatial dimension that also have interesting critical points, and whose behavior at the fixed point is described by CFTs that we'll also study later in the course, at least some of them. So now let's look at the example of quantum critical Hamiltonians. So the simplest example, perhaps, is the Heisenberg antiferromagnetic spin chain. The Hamiltonian, you know, again, has some energy scale. Sum over nearest neighbor. So this is now a one-dimensional chain, say a periodic chain. At its side, you have SU2 spin. Okay, so you have some spin variable sitting at its lattice side. Okay. These SIs, as you know, are, so forget about the index I. So there is essentially a set of 2x2 matrices at its lattice side. And these SG2 matrices are essentially the 3 Pauli matrices. So you have Sx, Sy, Sz, and these guys are just the usual Pauli matrices. Okay? So this model is also historically very important. It was solved exactly by Bethe in the 30s, using techniques which are called the Bethe ansatz. One of the fundamental properties that it has is exactly what I mentioned there, that if you compute the spectrum of excitations of this Hamiltonian, surprisingly, or not surprisingly, I don't know, that the gap is 0. So excitations are gapless. Okay? As a side remark, something also that's quite remarkable and that tells you about the mysteries of doing science is that exactly this Hamiltonian, that a priori has nothing to do with anything in some sense, is exactly, this Hamiltonian has appeared in the last 10 years as the Hamiltonian that describes the spectrum of operators, the spectrum of dimensions of operators in a very interesting theory that I already mentioned yesterday, which is n equals 4 super Young Mills. Okay? So somehow this problem also solves for you. And in your ADS50 course, I'm sure you'll see more about this. But solving this spin chain automatically gives you surprisingly information about some other interesting theory, which is this n equals 4 super Young Mills. Okay. But that's another interesting story that I don't have time to tell you, unfortunately. So now this quantum Hamiltonian, which is critical, is actually captured by a conformal field theory that we will describe. So the CFT description is going to be in terms of two-dimensional compact scalar field. So you're going to have a scalar field in 2 dimensions, phi. Phi is a scalar field. It's a function of x. But it doesn't live on the line. It lives on a circle. Okay? So you have periodic boundary conditions on the circle. But it's periodic with a very specific periodicity, where this radius is exactly 1/√2. Okay? And later in the course, we will see that, well, we will study the conformal field theory described by a compact scalar field. And what's special about this particular value of the radius is that at this point, this system has an obvious U1 symmetry, because you can shift phi by a constant. But I think that's miraculous, and which is not manifest just by looking at it now. But you will see it by doing a calculation, is that at this precise value of the radius, actually the theory that describes this compact scalar has an SG2 symmetry, which is precisely the symmetry of the Heisenberg spin chain. I mean, I imagine that it should be obvious that that Hamiltonian has a manifest SG2 symmetry under which you rotate all spins simultaneously by an SG2 transformation. Okay? So clearly, the conformal field theory will have to have the symmetry of that Hamiltonian. It just happens that in this description it's not manifest, but at this value you can show that there are extra conserved currents that fill an SG2 multiplet. Okay? There is another equivalent description of this conformal field theory that I will just mention, but unfortunately we won't have time to describe it in this course, but it's the beginning of a very interesting subject in itself. There is another description in which the SG2 symmetry is manifest, but perhaps the description in terms of the spin is less manifest, which is described by a two-dimensional CFT, which is called, if you heard the word before, and you will hear it again if you study high-energy physics or condensed matter physics, it's described by an SG2, what's called Wells-Domino-Witten model at level 1. So this right now is just a buzzword, but just to tell you that there is another representation of the critical behavior of the Heisenberg spin chain that uses a different class of conformal field theories for which this is just the tip of the iceberg. Okay? The other example I want to give you, and with that I'll conclude this part, is in the one-dimensional quantum Ising spin chain in a transverse magnetic field. So again, this is a spin chain in one dimension, like that. But now the Hamiltonian is a bit different. You have two-body interaction, as usual. But now you only have the Z component of the Pauli matrices. Okay, sigma set is the same as sigma 3, but that should be clear. And then you have a transverse magnetic field, like that. Now this system, in order to be gapless, so that if you want to close the gap and reach the critical point in the phase diagram of this system, what you have to do is you have to tune the magnetic field here to be 1, okay? And then the gap goes to 0, and you have a quantum critical phase, which will be described, as we will see also later in the course, by the two-dimensional conformal field theory of a free fermion in 2 dimensions. Okay? And this is just the tip of the iceberg. So I just wanted to give you a couple of concrete examples of a statistical system at finite temperature and in 2 dimensions, and of quantum Hamiltonians in 1 dimension that exhibit this interesting critical behavior And now in the last few minutes, I'll give you just a few other motivations for conformal field theory that maybe are a bit more modern or maybe not so traditionally mentioned. And with that, I'll conclude. And tomorrow we start with conformal transformation.
Question.
Yes.
On what does this SU2 have?
Excuse me?
This SU2 for a scalar field, on what does it act?
On the Hilbert space of the conformal field theory.
No, I mean, I don't see any two components.
No, but this would take me to a far afield, but let me just tell you in words, and then we will see it later in the course. You have a scalar field, so you can construct conserved currents out of the scalar field. And then you can ask what algebra do these conserved currents generate with each other? What commutation relations do they have? And what I'm saying is that the conserved currents that you can construct at this particular value of the radius generate precisely the SG2 commutation relations. But you have to construct a current associated to, so you have a U1, so SG2 has 3 generators, right? So you can phrase it as, let me say very quickly, but it's not, you have 3 generators, G plus, G minus, and G3. One is a Cartan generator, one is a ladder operator that raises spin, the other one lowers the spin. And in some sense, the currents here are partial phi. And it turns out that at this particular radius, you can construct an operator like that. And now, if you compute the commutation relations of these 3 operators, you find that they exactly satisfy the SG2 commutation relation. So you have an SG2 symmetry acting on your Hilbert space. But we'll come back to this. It's not. Okay, so why else? So there are several. I'll just mention 2. Is that one of them is that conformal field theory, 2-dimensional conformal field theory, again, describes the dynamics of relativistic string theory. So this is not a course on string theory, so I don't have much time to tell you about this, which is a pity, because it's a very beautiful subject. But the basic idea is simple, is that motion of particles is replaced by strings. So instead of having word lines, now you have 2-dimensional surfaces that tell you how a string propagates in time. Okay? And if you want to describe the dynamics of strings, how do you do it? It's described by precisely a 2-dimensional field theory living on the world sheet. Okay? So that's how we describe string theory, the dynamics of relativistic string theory in the perturbative regime. And it's more than that. Consistency requires that the 2-dimensional QFT to be actually a conformal field theory. Okay? So consistent propagation of strings in space-time, consistently with the rules of quantum mechanics, essentially unitarity, tells you that the 2-dimensional field theory living on the stream has to be a 2-dimensional conformal field theory. Okay? Furthermore, demanding that the theory is conformal gives you 2 amazing predictions, which are correct. There are many other ones that it gives you that are not correct, but this one is not correct. One of them is that the theory requires the existence of a spin 2 particle with exactly the same couplings as the graviton. Okay? So string theory predicts for you that you should see that in the spectrum of your theory, you should have a massless graviton with the couplings dictated at low energies by general relativity, which is an amazing prediction. Because before this framework, it was essentially impossible to put quantum mechanics and gravity together string theory forces you to put gravity in the game. You cannot forget about it. It's there, even if you're not looking. And the other one is that demanding exactly that the beta functions, so you have a two-dimensional quantum field theory. We have to fish for conformal field theories. Demanding that the beta functions of the two-dimensional field theory living on the string vanish gives you another remarkable set of equations. It gives you Einstein's equations of general relativity, plus systematic corrections. So there is a beautiful interplay between the beta functions equations of two-dimensional quantum field theory and gravity equations. Okay? And hopefully you will find out more about this in a future string theory course if you're interested in that subject. And the final thing I want to mention, there are more, but I don't want to kill you. Is that, oh, sorry. That actually conformal field theories, even in higher dimensions, are directly related to quantum gravity. So you probably have heard some of the buzzwords, so let me just tell you a little bit how conformal field theories enter there. So so we don't know much about quantum gravity, unfortunately, but I would say by far the best and our best understanding of quantum gravity is in the framework of the ADS-CFT correspondence. So CFT, now you know what those words mean. ADS means anti de Sitter space. This is essentially the maximally symmetric space with negative cosmological constant. So it's a space that satisfies something like this. Okay, this is the analog of flat space when your space-time has a negative cosmological constant. And this space-time has the following unusual property. Roughly speaking, it looks like a cylinder, a finite cylinder, finite in this direction. It's not really finite in terms of distance, but it's finite in the sense that if you shine light towards the boundary, so there's a boundary in the cylinder, this is like a can of soup, so there's a boundary. If you shine light, even though the proper distance is infinite from any point here to the boundary, light shines back from the boundary in a finite amount of time. So in some sense, ADS is like a cavity. It's really acts like a finite box. And this correspondence tells you that in the bulk, you can have quantum gravity. You can have black holes, whatever quantum gravity is all about. And the ADS correspondence essentially tells you that everything that can happen inside this box, which is quantum gravity with these boundary conditions, with anti de Sitter boundary conditions, is precisely captured. So if this is anti de Sitter space, say, in d+1 dimensions, so you have gravity in d+1 space-time dimensions, the physics inside this box, the statement is precisely represented by a conformal field theory in d dimensions, in one less dimension. Okay? And this conformal field theory, exactly the types that we will describe in this course, resides at the boundary at infinity of this box. Okay? And by far, since we understand much more about conformal field theories than quantum gravity, by far the formulation of all the dynamics that can happen in the interior of the box in terms of conformal field theory has given us the most precise descriptions about quantum gravity phenomena that can happen, at least asymptotically into the de Sitter space. So later in the course, I think you'll have in the year, you'll have a course on ADS-CFT, where hopefully you will see how beautiful this dictionary is between gravity in the box and correlation functions of operators in the boundary CFT. So there are some other things I could say, but I probably leave them for some other time. And I'll probably stop, and tomorrow we'll continue by starting more systematically with the construction of CFT. Any questions? So this ends the motivation part of the course.